So the last thing in this chapter is the inverse of a relation. You saw this in 20-1. You did some work with inverses of quadratics. So it's going to be the same principle and process. So we'll look at sketching the graph of the inverse of a relation. We'll determine if a relation and its inverse are functions, and then also determine the equation of an inverse. So on the next page, the inverse of a relation is found by interchanging the x coordinates and the y coordinates of the ordered pair of a relation. In other words, for every ordered pair x comma y of a relation, there is an ordered pair y comma x. So you see x comma y becomes y comma x. You switch the x and y around. This means that the graph of a relation and its inverse are reflections of each other in the line y equals x. So we've seen about reflections across the x-axis, across the y-axis. So that's why this is a part of a transformation. It is a reflection. The only difference is that the reflection is about the line y equals x. So we saw before that when a graph reflects over the x-axis, the x-intercepts were invariant. When the graph reflected over the y-axis, the y-intercept was invariant. In both cases, the invariant points are on the line of reflection. So when you take the inverse, there will be invariant points, potentially, as long as there are points on the line y equals x. The invariant points occur on the line of reflection. So the inverse of a function y equals f at x may be written in the form x equals f at y. The inverse of a function is not necessarily a function. Remember, a function is a relation that passes the vertical line test. Every point on that graph has a different x value. Because if you have points that have the same x value, you would be able to draw a vertical line that would cut that graph in more than one spot. A function is a relation where every point has a different x value. Therefore, wherever you draw a vertical line, it'll only cross the graph in one spot. But we're going to see that in some cases, a function will have an inverse that is not a function. It would fail the vertical line test. When the inverse of f is itself a function, it is denoted as f to the negative 1 and read as f inverse. When the inverse of a function is not a function, it may be possible to restrict the domain to obtain an inverse function for a portion of the original function. So we'll talk about that today. The inverse of a function reverses the processes represented by that function. Functions f at x and g at x are inverses of each other if the operations of f at x reverse all the operations of g at x in the opposite order, and the opposite operations of g at x reverse all operations of f at x again in the opposite order. So the inverse will reverse the order of the operations. So it's like it's in the opposite order. So for example, if f at x equals 2x plus 1, if that's your function, well, you would take your input values, your x values, and multiply by 2 and add 1. The inverse does the opposite operations in the opposite order. So the original function, you'd multiply by 2 first, you'd add 1 second. The inverse does the opposite operations, but also in the opposite order. Instead of by adding by 1 second, you'd subtract by 1 first. And instead of multiplying by 2 first, you take half second. So opposite operations in opposite order. So that is true, but that's not how we're going to get the graph of an inverse. We'll do it using an algebraic process that I will show you. Okay? So if you have that graph y equals f at x, and you wanted to sketch the graph of the inverse, the simplest way to do this is to take points on the original graph and switch the x and y values around. That was the very first thing that we started with when we talked about inverses. X comma y becomes y comma x. It is true that the result of the graphs will be reflections over the line y equals x, but normally that's not the easiest way to graph it. Normally the easiest way is to take points on the original graph and reverse them. So the original graph has points negative 6 comma 0, negative 4 comma 2, negative 2 comma 1, and 0, 3. So to get the points on the inverse, you would just switch them around. So negative 6, 0 becomes 0, negative 6. Negative 4, 2 becomes 2, negative 4. Negative 2, 1 becomes 1, negative 2. And 0, 3 becomes 3, 0. The original graph is a series of lines that are connected, so the inverse will be as well. Did I write down the wrong? Negative 1, 3. Yes, thank you. Thank you. So this was negative 1, 3, and it became 3, negative 1. There we go. So there's our new graph. And they are reflections about the line y equals x, which goes through 1, 1, 0, 0, 2, 2, negative 1, negative 1, and etc. Whoops. Okay, something like that. So what it means when it's reflected about the line y equals x, just like when we reflected graphs about x and y axis, corresponding points are the same distance away from that line, but on the opposite side. And because in this case, if you were to measure the distance from each point to the line y equals x, you're measuring across a diagonal. Sometimes it's not so easy to count how many units away one point is from the line y equals x and then reflect it over. Sometimes. Not quite so easy to do that. The easiest way is to take points on the original graph and switch them around. Okay? So on this next page, we're asked to graph the inverse. We'll state the domain and the range of both the relation and its inverse, and then determine whether the relation and its inverse are functions or not. So if we just take that original graph first, the original relation, and let's state all those characteristics. The domain would go from negative 6 to positive 6. So I'm going to use integral notation for this. That's by far the easiest way. And again, those brackets at the end are squared because those n values are part of the domain. They are included. The range would go from a minimum of 0 to a maximum of positive 6. And it is a function. It passes the vertical line test. There's nowhere you could draw a vertical line that would cross that graph in more than one spot. No matter where you drop this vertical line, it's going to cross the graph in only one spot or no spot at all. To say it's not a function, that vertical line would have to cut the graph in more than one spot somewhere, and it doesn't. So let's graph the inverse now. So the point negative 6, 4 becomes 4, negative 6. The point negative 4, 6 becomes 6, negative 4. The point 0, 6 becomes 6, 0. Now, that point is common to the original, to a point on the original graph, but it's not considered to be invariant because the point came from a different place. It moved. Yes, it became a point that was part of the original graph, but it's not invariant because it came from a different spot. It moved to get there. So then we have the point 2, 2. That is a true invariant point because when you switch the 2's around, you get exactly the same point. It is on the line y equals x. So it is a true invariant point. Okay, next we have 4, 2. That becomes 2, 4. And then we have 6 comma 0, that becomes 0 comma 6 again. That was a point on the original graph, but it is not an invariant point because the point moved to get there. So we can join all these with a series of lines. And there's the new graph. They are reflections about the line y equals x. But it would be really difficult to get your new graph by taking points on the original graph and trying to reflect them over that line y equals x. Really difficult. So that's why we don't use that method. We take points on the original graph, switch them around to get our new points. So the domain of the new graph, it goes as far left as the y-axis, where x is 0, and as far right as positive 6 on the x-axis. So the domain goes from 0 to 6. The range goes from a minimum value of negative 6 up to a maximum value of positive 6. So again, we found our new points by switching x and y around. And notice that the domain and ranges are switched around. The domain of the relation is the same as the range of the inverse. The range of the relation is the same as the domain of the inverse because x became y and y became x. So it makes perfect sense that the domain and range of it also be interchanged. And this one is not a function because if you drop that vertical line right there, it'll cross the graph in infinitely many places. Same thing if you drop that line right there. All you have to do is find one spot where a vertical line crosses the graph in more than one spot, and you can say it's not a function. So the inverse is not a function. It fails the vertical line test. There are lots of places where different points share the same x component. So again, it talks on the bottom there about that horizontal line test, a test used to determine if the graph of an inverse is a relation. It is possible, if it is possible for a horizontal line to intersect the graph of relation more than once, then the relation, the inverse is not a function. Your name is? Jackson? Are you new? What's your last name? How do you spell that? M-O-D-L-L? And Dan? His first name was again, sorry, Jackson? You just get added today? Okay. So you'll have to go to the library at some point and get a textbook. Okay. There's a white package over there you can grab on that shelf. Okay. So consider the graph of the relation shown, exact same type of question that we did last. This one also asks for a mapping notation. So we'll talk about that as well. So looking at that original graph, the domain would go from negative 6 to positive 5. The range goes from 0 up to 4. And that original relation is a function. No matter where we draw a vertical line, it'll only cross the graph in one spot, no matter where we stop and drop that, or it won't cross it at all. Yeah. Oh boy. Thank you. Over on the corner of the filing cabinet. Actually, just give it to me here. Thank you. Okay, so to get points on the inverse, the point -6, 0 becomes 0, -6. The point -4, 4 becomes 4, -4. The point 0, 4 becomes 4, 0. Once again, the point 2, 2 is there. That will be an invariant point because the point did not move to get there. Lastly, 6, 0 becomes 0, 6. Sorry, not 6, 0, 6, 2 becomes 2, 6. So you can see we've got a couple sections of this graph that are vertical, so therefore it is not a function. It will fail the vertical line test. If we drop the line there, it's crossing the graph and infinitely many points. Same thing happens there. So it doesn't matter which place you look at, all you have to find is one spot where the graph crosses a line in more than one place, and you can say that it is not a function. Also, if you look at the domain of this graph, it goes from 0 to 4, which is the range of the original relation. And the range of the new graph goes from -6 to 6, which again is the domain of the original function. The original relation was a function, but the inverse was not. It doesn't always happen that the inverse is not a function. You have to look at each one separately. Now the mapping notation would look like this. X comma y would map into y comma x. That's how we got all the points. We took the x and y values and we switched them around. So the mapping notation is the same thing. Okay? So now we're going to sketch the original graph and then do the inverse. And we'll talk about whether it's a function or not. We'll also do the equation of the inverse and as well a mapping notation. The mapping notation will never change for the inverse. We'll do that right now. X comma y maps into y comma x. The original graph, the graph of y equals x squared minus 2. That's the graph of y equals x squared shifted down 2 units. So instead of having a vertex at 0, 0, it'll be at 0, -2. Instead of going through -1, 1, it'll go through -1, -1. Instead of going through -2, 4, it'll go through -4, 2, -2, 2, I should say. We're just moving all the points down 2 units. So here's our original graph, which is a function. It passes the vertical line test. So to sketch the graph of the inverse, we'll take points and we'll switch them around. The point -2, 2 becomes 2, -2. The point -1, -1, that's going to be invariant. There is an invariant point here. The point 0, -2 becomes -2, 0. The point 1, -1 becomes -1, 1. And the point 2, 2 will be invariant as well. There are 2 invariant points here. And obviously the inverse is not a function. It fails the vertical line test. So part C, well, first, is the inverse of f of x a function? We can say no, because it's not. But part C, describe how the domain of f of x could be restricted so that the inverse would be a function. And here's what we could do. If you just took the left side of the original graph by itself, if you restricted the domain of the original function and said x had to be less than or equal to 0, that would just give you the left side of the original graph. If you took the inverse of just that part, it would become only the bottom of the new one. So let me change the color of the highlighter. It would become only the bottom of the inverse. And by itself, the bottom without the top is a function. If you forget about the whole top part of the graph and only look at the bottom, by itself, it is a function. Once you add the top part, it's no longer a function. So we could restrict the domain on the original graph and say that x must be less than or equal to 0, which would give us only the left side of the original graph, which would give us only the bottom of the inverse. The bottom by itself is a function. So that is the restriction on the domain we could use here. Or we could also say x must be greater than or equal to 0. That would give us only the right side of the original graph, which would become only the top of the inverse. And the top by itself, without the bottom, is also a function. So that is how we can restrict the domain on the original relation so that the inverse is also a function. Now, to get the equation of the inverse, we'll start with the fact that the original equation was x squared minus 2, y equals x squared minus 2. Remember, to get points on the inverse, you switch x and y around. So we'll do the same thing to the equation to get the equation of the inverse. Our first step is to switch x and y around. The original equation had y by itself. The inverse has x by itself. The original equation had the x squared. The inverse has the y squared. That is our first step, but we're not done because now we want to get the equation in its original form, which is the form y equals. So if you add 2 to both sides, you'll get the y squared by itself, and then we'll take the square root of both sides, and you have to remember whenever you're solving an equation, which is what we're doing here, we're solving for y, getting y by itself. Whenever you take the square root of both sides, there's always a positive and a negative root. So that is the equation of the inverse. Now, just to show you why you need the plus and minus there, if we go to our graphing calculator and we put in our original equation, x squared minus 2, zoom 6 to set my windows to their standard settings, there's the graph. If in y2 you just put the positive root of x plus 2 and graph that, you see it only graphs the top part of the inverse, not the bottom. You'll need a third equation in there with the negative root of x plus 2 to get the entire inverse graph. Now it graphs the bottom as well. So this is just verifying that you need the plus and the minus on the root of x plus 2 to get the entire equation of the inverse. But it started by switching the x and y value around. That's always your first step when you want to graph an inverse. Switch the x and y around and then solve for y. Okay, so now we've got the graph of f at x equals x plus 2 all squared. So that is the graph of y equals x squared shifted 2 to the left. That's an h value of negative 2. Remember, whatever happens to the x happens to the x minus h. The x is squared, so the x minus h would be squared as well. That's one way we know that that 2 is connected to an h value. Also, h is hooked on to the x with a plus or a minus inside brackets. Right, that's another way we know that that 2 represents an h value. But remember, the value of h is always the opposite of what it appears to be. H is -2, the graph will shift 2 to the left. So instead of going through 0, 0, it'll go through -2, 0, shifts 2 to the left. Instead of going through -1, 1, it'll go through -3, 1. 1, 1 will shift 2 units to the left and become -1, 1. -2, 4 goes 2 to the left, and 2, 4 goes 2 to the left. So here's our new graph. Or not our new graph, the graph of the original relation. So to get points on the inverse, we'll take the original points, switch them around. -4, 4 becomes 4, -4. -3, 1 becomes 1, -3. -2, 0 becomes 0, -2. -1, 1 becomes 1, -1. And 0, 4 becomes 4, 0. And obviously that is not a function. It fails the vertical line test. In this case, there are no invariant points. All the points changed. Remember, if there were, they would be on the line y equals x. The two graphs are reflections about the line y equals x. So if there are invariant points, they will be on this line. Judy, you with us? Okay, good. Okay, so the inverse is not a function. But we can restrict the domain on the original relation so that the inverse is a function. For example, if I took the left side of this graph only, that would correspond to the bottom of the inverse only. And the bottom by itself is a function. Without the top on there, a vertical line would only hit that graph in one spot. Similarly, we could take the right side of the original graph only, which would correspond to the top of the inverse only. The top by itself is a function. So the restriction on the domain that we could do here would be, in this case, that x had to be less than or equal to -2, because that's where the vertex of this graph is. It's at -2, 0. The last one was at 0, something, 0, 2, if I remember correctly. But in this case here, it's at -2, 0. So the left side of this graph is only where x is less than or equal to -2, or we could also say x is greater than or equal to -2. Either one of those are the answers to the restrictions that would make the inverse a function as well. Right, to get the equation, we start with the original graph. Y equals x plus 2 all squared. And our first step is to switch x and y around. X becomes y, y becomes x. And then we want to get y by itself. We're going to square root both sides. But remember, when you take the square root, it's always going to be a plus or a minus. When you take the square root on the right, it cancels with the square. And then you would subtract 2 from both sides. So it will become a -2 on the other side, plus and minus root x. So, just to confirm, we start with the original graph of x plus 2 all squared. And we can see what it looks like, make sure it matches what we graphed, or make sure what we graphed matches what the calculator gives us. If you just put -2 plus root x in your calculator and graph that, It only graphs the top of the inverse. You have to put another equation in there, negative 2 minus the root of x, to get the complete graph of the inverse. And that matches what we did on our graph. Okay? This one doesn't ask us for the mapping notation, but it would just be x comma y maps into y comma x. So it asks us to algebraically determine the equation. So again, that means you got to show your work, show your steps. Also graph, verify that the relations are inverses of each other. So that first one, that's a line, y equals 3x plus 6. That has a y-intercept of plus 6 and a slope of 3. That's 3 over 1, because remember we always talk about slope in terms of rise over run. Now we don't have room to rise 3 because our y-intercept is already at the top of the grid, but that is the same as negative 3 over negative 1. You can rise negative 3 and run negative 1. Rising negative 3 takes us down 3, running negative 1 takes us 1 to the left. We can do it again. Down 3, left 1. Down 3, left 1. Down 3, left 1. All these points line up. And there's the line of y equals 3x plus 6. Our graphs always have arrows on the end when you graph from an equation. The pattern continues forever. Okay, to get the equation of the inverse, instead of y equals 3x plus 1, it'll be x equals 3x plus 1. And then you want to get y by itself. Subtract the 1 from both sides and divide by 3. Wow, I don't know what's wrong with me today. Thank you very much. So we subtract the 6 from both sides and divide by 3. So you could write it like that. And we talked about this at the start. The inverse does the opposite operations in the opposite order. If you started with the original function, f at x equals 3x plus 6, you'd start with numbers for x, plug them in, you'd multiply by 3 and add 6. Multiply by 3 first, add 6 second. The inverse does the opposite operations in the opposite order. Instead of adding 6 second, you subtract 6 first. Instead of multiplying by 3 first, you divide by 3 second. Okay. This could also be written as 1/3 x take away 2. If you divide each term on top by the 3 on the bottom, you could also write it like that. Which you would want to do to help you graph it from the equation. You could also graph it by taking points on the original graph and flipping the x and y values around. But in this case here, if I graph it from the equation, that graph has a y-intercept of -2 and a slope of 1/3. So we rise 1 and run 3. Rise 1 and run 3. We could also rise -1 and run -3. Rise -1 and run -3. That works as well. So this is the graph of the inverse. And they are reflections about the line y equals x. The invariant point, there is one there at -3, comma -3. It is on the line of reflection. And we can verify just by taking some points on the original graph and switching them around. The point 0, comma 6 became 6, comma 0. That works. The point -1, comma 3 becomes 3, -1. That's on there. So on. All right, question B, to get the equation, instead of y equals, it'll be x equals y squared take away 4. We'll add 4 to both sides. and then take the square root of both sides, and when we do that, we'll get the positive and negative root of x plus 4. We'll graph the original relation. That's the graph of y equals x squared shifted down 4 units. So instead of being at 0, 0, it'll be at 0, negative 4. Instead of being at negative 1, 1, it'll be negative 1, negative 3. Negative 2, 4 becomes negative 2, 0. 1, 1 becomes 1, negative 3. 2, 4 becomes 2, 0. So here's our original graph. So to get points on the inverse, negative 2, 0 becomes 0, negative 2. Negative 1, negative 3 becomes negative 3, negative 1. 0, negative 4 becomes negative 4, 0. That's our new vertex. 1, negative 3 becomes negative 3, 1. And 2, 0 becomes 0, 2. And in this case, the inverse is not a function. We could restrict the domain of the original relation by saying either x is less than or equal to 0. That's the entire left side of the graph. The inverse of that would become the top of the new one. That would work. Actually, it would become the bottom, excuse me. Or we could say that x had to be greater than or equal to 0, which would be the top only. And that would work. So the original function f at x equals x plus 8 over 3. That would be the same thing as 1/3 x plus 8/3, which we might do to help us graph it using y equals mx plus b. You are going to have to kind of guesstimate where that y-intercept is because 8/3 is 2 2/3. So you kind of guesstimate where that would be, approximately right there. And the slope is 1/3, so we can rise 1 and run 3. We have room to rise 1 and run 3 one more time. We could also rise negative 1 and run negative 3. Rise negative 1 and run negative 3. That works as well. Again, we have to kind of estimate where that y-intercept is, and that's fine. So there's the original graph. To get the equation of the inverse, we'll start with y equals x plus 8 over 3. And you start by switching x and y around. To get y by itself, I would multiply both sides by 3. That gets rid of the denominator of 3 on the right. And then subtract 8 from both sides. So there's the equation of the inverse. Note that for the original graph, you would add 8 first and you would divide by 3 second. The inverse does the opposite operations in the opposite order. Instead of dividing by 3 second, you'd multiply by 3 first. Instead of adding 8 first, you'd subtract 8 second. Opposite operations, opposite order. This graph would have a y-intercept of negative 8 that we don't really have room for on our grid, but we can kind of guess where it would be, somewhere down there, and a slope of 3. So you'd rise 3 and run 1. 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 So this line would look something like this. Okay, and in this case, both the relation and the inverse are functions. Okay, so there's an assignment there in the package that you can work through. I would encourage you to do that. I will post the solutions to Google Classroom so you can check your answers, but you're going to do the quiz first that I'll hand out. So once you're done the quiz, you can just put it on the corner of the filing cabinet there and then get to work on the assignment. Okay?